ಇದೆ. We have seen some part of it. So this is the PPP modeling, and then we have SINR definition. Just to review, we have already seen this, and we have two pre-coding schemes here. One is zero forcing and second is MRT. So this factor of M is the error gain here.
Yeah, he's showing the channel hardening over there.
Yeah, this is the channel hardening. If we have a multiple antenna receiver, we will have identity instead of one here. Okay. And this is the theorem to find out the success probability in terms of physical layer parameters. Then we have this interference limited case. If we have interference limited case, we can find out the nice expression in terms of this A, B, and C parameter. And the success probability is independent of the density of base station and user. This is what we have concluded yesterday. So next we have presented this approximation e to the power minus x equals to 1 minus x. In this expression, if we put it, we will get some approximation for GQF that is given by like this, and if we average over all files, we will get some expression like this. We will use this expression to propose one Q-learning algorithm. Okay. So this is the general idea. We have seen the terminology. Okay. After the terminology, we seen this toy example. This is the update equation. This is all we have seen yesterday. Okay. So just to review. Okay. So this is the update equation that is very important. You need to remember that if you are working Q-learning. Okay. So this is the algorithm for Q-learning. Now let's come to the edge caching. So for this, we have also code to implement this, whether at any particular block, if we are there, how to move so that we can reach the terminal state as soon as possible. Okay. We will also show here. Okay. After this slide completes. So Q-learning for edge caching. So Q-learning happens in a dynamic manner. So also in like the time slots. So this is the T minus 1 time slot, and this is T8 time slot. In the T minus 1 time slot, we have CD, IE, and CP phases. CD means content delivery phase, IE means information exchange phase, CP means content placement phase. So content delivery means when we have already cached the content in our cache from the previous time slot, we will deliver the content during the peak period. Okay. Information exchange phase comes when we have off peak period. So we then exchange the information with nearby base stations so that we can find out what is the true content popularity. So at this point of time, the present content popularity PT minus 1 is unknown, and when we exchange the information, we will get PT minus 1. Okay. Then we place the content accordingly. Okay. When we have this information available, we can calculate the average success probability, and to maximize the average success probability, we can place the content accordingly. Okay. So similarly, we can do in the next time slot. In the content delivery phase, whatever we have placed the content previously, we will deliver accordingly in the peak time. In the off peak time, we will do the information exchange and content placement. Okay. So we model our edge caching problem in terms of Q-learning. So we have to define the terminology for the Q-learning for the edge caching problem. Okay. So in the Q-learning, we have a state. So state we are defining as PT and QT. PT is the popularity profile, and QT are the caching probabilities at the base station. Action set we are defining as QT. So we have to find out QT so that we can place the content accordingly among the base station. QT are the network caching probabilities. Okay. CST is the cost we are defining the cost in terms of average success probability. Okay. So in Q-learning there are two terms sometimes comes, cost or reward. If we are writing cost here, so cost is to be minimized. If we are writing reward here, it means is to be maximized. Okay. So if I write here reward, I can write here just PS, that is the average success probability, and I will want to maximize that. Now here I am writing cost, it means I want to minimize this. Next we have policy function. Policy function pi which maps states to action. Okay. So let's say we have the grid, right? Earlier grid example, whatever we have state, which action to take, this policy function tells us. Okay. So given the state, it will tell us what action to take. So state value function v pi, we can define like this in terms of cost. Okay. This is also to be minimized. So the objective function is to find the policy, that is this mapping pi which maps state to action such that it minimizes the long term average discounted cost, that is v pi, this equation. So we use Q-learning to obtain the optimal policy by this. Okay. So this is the Q-learning procedure. So first we initialize the state randomly and we set all Q values to 0. So Q values will be a matrix. So we initialize that matrix to be 0, and for each round we learn, for each time we learn. So when the content delivery takes place, then do the following. So we have three phases, right? Content delivery phase, information exchange phase, and CP, that is content placement phase. So after content delivery is done, what we do, information exchange. So after information exchange, we will know the popularity profile, which is revealed based on the user request. Okay. Then we find out the state, what is the state of the present system, and we compute the cost in terms of ASP. Okay. Then we update the Q is what? The Q values. We update the Q values using the Q update equation that we have seen earlier. Okay. And after that we will do the content placement. For the content placement, that is the action, we will choose the epsilon greedy action. Okay. So this is the way we choose the epsilon greedy action. So random Q means we will choose random value for the this action, or here we will choose random values according to the Q values. Okay. So this is the way we define the epsilon greedy. We have seen this as similar for the grid problem also. Okay. And the same thing goes on. So this diagram shows the similar thing in a like block diagram form. So popularity profile are changing, and if we take some action, that's a QT, it means we are taking the content placement and we have placed the content. Then after content is placed, in the next time slot content delivery takes place. After the content delivery, information exchange takes place, and after the information exchange, next PT is revealed. And in this process we will get the cost based on the current cache content and whatever the popularity is there. Okay. That will be used to update the Q values. So this is the conventional Q learning. So conventional Q learning has some disadvantages. The disadvantage is that the size of Q matrix goes with P into A square. So P is what? The size of states and action. So Q here, if you see here, so we have this P and Q state. So it has these two. Okay. So size will be, so total number of states will be the dimensionality of this, dimensionality of this, and Q also comes state and action. So action is QT. So size of this. So dimensionality of P into dimensionality of A squared. So that is the size of Q matrix. So if we increase the number of actions, it will grow exponentially for this problem. Okay. So this cannot be used for scalable transition. I mean like scalable file library, because in edge caching we have big file library. Okay. So we cannot use for larger, and it is the higher search complexity. So for example, here we have to search for the greedy action. If my file library is large, if we have large number of actions, it will take longer to search here. Okay. And higher search complexity and slow convergence. So if we have larger set, larger matrix Q, so we have to fill each and every value for the Q matrix, and it will take very long time. So it will have slow convergence. Okay. So these are the disadvantages for conventional Q learning. So what we come up with, Q learning with function approximation. Okay. So in this approach, so linear function approximation is a popular method in Q learning to applicable for the real world setting. So what we do, we approximate this Q by some function that is linear. Okay. So here we have this theta 1, theta 2, theta 3 and theta 4, 4 linear coefficients. Okay. Now how do I approximate this? So recall that Q is made of cumulated discounted cost, okay, and cost is made of this ASP, average success probability, and average success probability I have derived an approximation for that. Okay. So in that approximation, whatever term I have put the theta here. So that will make a linear function of theta here. So this Q is linear function in terms of theta. So that's why this is a linear function approximation. Okay. Now what is the advantage of it? Now if here I have written in terms of this vector form. So theta is a vector, U is a vector. So U is a vector consisting of all the remaining quantities. Okay. So what is the advantage of it? Here, instead of updating Q, the whole matrix, I can just update my theta here, and it will update the whole matrix. Okay. If I update my theta, one theta, and it will update my whole matrix. Okay. So it will not take longer to converge, and I will get reward from the start, some good rewards instead of zeros. So my matrix is filled with some values from the start as soon as theta gets some value. Okay. So that's the idea for linear function approximation. And similar to Q updates, the gradient descent can be applied for the theta update equation, and we can write this equation like this. Okay. Where delta t is the same temporal difference that we have seen earlier, and global convergence with linear approximation has been proved in the references also. So we can also do nonlinear function approximation also. So here we have taken 3 variables. So because our action is A is related to Q, caching probabilities, what to cache. Okay. So I have put theta here and theta here where the Q is, okay, and theta here. Okay. So this will give me the nonlinear function approximation, because now it is not a linear function in terms of theta. Okay. So this is nonlinear function approximation. If you are taking another measure, you can also come up with another approximation, and you can use theta differently. Okay. That will be another approximation. So each of the coefficient is associated with the action Q, f t plus 1. Okay. So these are the update equation, the similar update equation, and we have derived the values for here. Okay. The convergence is also proved in this paper for this particular algorithm. Okay. So number of updates in edge caching scenario, we have number of states times number of action. With linear function approximation, we need to update only 4 variables. So it is independent of number of states, number of action. That is a huge big advantage here. And Q learning with NLFA, I have chosen only 3 variables. Okay. So both of these algorithms are very good in terms of complexity also and updation also. Storage wise also good, because if you have to store the whole Q matrix, now you have to store only the 4 variables. And whenever you want to calculate that entry, just go to calculate those entry using those 4 variables. Okay. Another advantage is function approximation approaches the better immediate intermediate rewards before convergence. So Q learning converges like this. So in the between, Q values are not filled. So it will not give better reward. But theta, as soon as we have theta, the Q matrix will be filled whole, and we will get better rewards from the start. So these are some simulation results. So here we update one entry of Q at a time. So the here we see the convergence. So Fs has seen finite state and finite actions. Okay. So and this is linear function, non-linear function, and this with ASP. So here we have the reward, and here we have average ASP. I mean, here that is the cost what we have assumed. Okay. So we see that it learns very smoothly if we update one entry of Q at a time. Okay. In both of them. So in the left we have 256 states and 32 action. In the right we have more states and more actions. So with the single Q entry update, so we are updating only one entry. Even if we are choosing function approximation, we are updating Q entry. So what we are showing here is that both of the algorithm with function approximation also, we are achieving the similar performance, even if we update single entry. Okay. So here we are seeing the average mean squared error per episode. Okay. So that is very low for the non-linear function approximation, and linear function approximation, it is going a little bit high, and you see it is 10 to the power minus 3. That is very good. It means we are reaching convergence very good. And for the conventional learning, it is still high. It is in like 0.1. Okay. So these are the result when we update all Q entry one at a time. So normal Q learning, it's like this. But if we use the linear function approximation or non-linear function approximation, the Q entries are updated from the start. As soon as theta has some value, theta is updated. Okay, so we are getting rewards from the start, and it goes like this. So it means we are reaching convergence early also here. Okay. So this also shows the average mean square errors similar to this previous slide here. So it shows a similar result that for NLFA, non-linear function approximation, we are reaching the convergence very low. Okay. So this shows the result with the cache size, the converged value. Okay. So we can see this linear function approximation, this red non-linear function approximation approaches the conventional Q learning, and LF is approaching little bit below when the cache size is low. Okay. And for high cache sizes, the all results are approximately similar. Okay. So this is the summary of whatever we have talked about for the edge caching. We have we have shown you this online prediction method. Two methods were there: PPM, popularity prediction model, and GPM, Grassmannian prediction model. And popularity prediction model is good for minimizing the MSE, and GPM is good for maximizing the ASP. WFTL method, that is the online learning method, it is good for minimizing the MSE regret. And W4L method, that is good for the minimizing ASP regret. And we verified the performance on movie lane dataset. And for a PPP cellular network with lower content popularity model as finite Markov chain, Q-learning we have used. We have seen function approximation method which converge and require a constant number of variables to be updated. And we have also verified the performance of all of them. Okay. So these are some papers. Thank you. Okay. So so now let's see some simulation result related to this Q learning. Okay. So I will show three programs. In the first program, I will show you the Q learning, how we do Q learning in that toy example, grid world. Okay. In the second program, I will show you how to do conventional Q learning in the edge caching. In the third program, I will show you how to do function approximation in edge caching. Okay.